Good afternoon, Madam Karunisa. I am Mishka and now I'll be presenting on the introduction. In this project, we use sunlight as our main energy source. The solar panels will then convert the sunlight into DC electricity, which is then regulated by a DC-DC boost converter with MPPT. The MPPT ensures that the solar panel always operates on their maximum power point, even when the sunlight condition changes. The regulated power is then sent to a solar charge controller and then stored into a deep cycle battery, providing backup energy during the cloudy weathers. Also, an off-grid inverter then converts the DC power into a 230 voltage AC to drive the water pump. This pump automatically supplies water to the irrigation system based on the agricultural needs. Our main goal for this assignment is to design and simulate a system which is reliable, cost-effective, and also environmental friendly using the Simulink MATLAB. By relying on renewable energy, the system reduces operating costs, produces zero emission, and also ensures a continuous water supply for farming. There are few objectives for this assignment. First of all is which we need to design and simulate a solar PV system using MATLAB Simulink. And then we need to model key components such as PV array, determining the size from a datasheet, the DC-DC converter, which we need to design the inductors, capacitors, and also the duty cycle with the MPPT, and then the battery size, and also an inverter to convert from DC to AC. It is to ensure the system can supply power to an AC load. And lastly, it is to analyze energy conversion, efficiency, and the overall system performance. Now I'll be presenting on the design of solar panel. We use a solar panel for the datasheet of Senko Power. The output power we use is about 450 watts, and the voltage we use is 34.67, following by a short circuit current of 13.89 and a module efficiency of 3%. There are also some assumptions made, such as the panel generation factor of 1.3, the peak sun hour depending on the location of the agriculture uses about 4.7, and the battery voltage is about 48, the inverter size is about 20%, and also the battery loss and the depth at discharge, which is constant 0.85 and also 0.86. This is the size we use to determine the solar panel. Next, I'll be talking about the appliances which solar panel is needed for. First of all is a solar water pump which supplies water for the water irrigation, and next the water irrigation fan system which prevents overheating, LED lights which provides illumination during low lights, and lastly the sensor controller which is used for the automated irrigation. And has seen beside that the calculations of solar panel. After calculating, the total appliances seen is 144 kilowatts per day, and also we calculated the total modules needed for the solar panel is about 9 modules, and for the inverter size is about 3 kilowatts, and battery sizing is about 800 mAh, and also the solar charge controller size which needs about 170 ampere. This is for me. Thank you.
Okay, so I'll be presenting for DC-DC converter design. My name is Irfan. So before our design, we need to calculate for our wanted appropriate parameters for our inductance, resistance, capacitance, and also our duty cycle. And firstly, we want to calculate for our wanted output voltage, which is 400 V. So firstly, we need to calculate our initial V in, which is NS times voltage at max power, and then after that we can calculate our resistance from the formula P equals to V squared over R, and then we can also use V out over V in equals to 1 over 1 minus D to find our duty cycle. After that, we can also assume our voltage ripple, which is equal to D over RCFS. For this case, we use the voltage ripple at 2%, which is 0.02. After that, we can calculate our critical inductance from the formula L critical equals to RD bracket 1 minus D bracket square over 2 Fs. After we find the critical inductance, we can times it with 100 to find our inductance of the DC-DC converter system. So after calculation, we have obtained our wanted parameters for the cycle. This is for output voltage of 400 V. for duty cycle, we got 0.337. For resistance, we got 57.14 ohm. Inductance, 42.3 mH. For capacitance, 29.49 millifarad. And for our switching frequency, we set it at 10 kilohertz. And for the design, for the MATLAB design, you can see at the picture given. This is our MATLAB design for DC-DC converter system. And all the resistor, inductor, and capacitor use the values we obtained from the calculation. After that, we calculate again, but this time we change the output voltage to 325 volt. After the calculation, we got this duty cycle 0.184, resistance 37.7 ohms, inductance 23.1 mH, capacitance 24.4 millifarad, and for switching frequency is the same as we set at 10 kilohertz. So and also uh, the system of the DC-DC converter, boost converter, we set at in MATLAB is also the same as the 400 volt. uh, as you can see, we set the irradiance and the temperature constant. Irradiance at 1000, and for temperature is at 25 degrees Celsius. And the system is also equipped with a lot of measurement sensors to deduce the value of the boost converter that we wanted, the value that we wanted.
Next, I will explain the inverter section of our system. Our inverter is full bridge hash bridge design consisting of four MOSFET switches. Leg A is formed by S1 and S2, while leg B is formed by S3 and S4. These switches operate in complementary pairs to prevent shoot-through and to alternate the direction of current flowing through the load. The switching action is what generated by AC waveform from the DC input. The DC input to the inverter is around 300 to 350 voltage, which is the special one is 3 to 5 volt, supplied by the boost converter using sinusoidal pulse width modulation. We compare a 50 Hz sine reference with a high frequency triangular carrier to create switching pulse. This allows the inverter to produce a PWM output whose fundamental component is a 50 Hz sine wave. The effective AC output is controlled by the modulation index using the formula Vrms equal to M times VDC over root 2. With our DC link and modulation index, we achieve the required, which is 230 volt RMS output. On the right, you can see the output statistic from our simulation. The inverter successfully produced a 50 Hz waveform with an RMS value close to 230 volts. The waveform plot below shows the filtered output after the LC filter, which is to remove high frequency harmonics and give us a clean sinusoidal AC signal suitable for powering of our load. In summary, the inverter efficiently converts the boost DC voltage into stable 230 volts AC using SPWM and H bridge topology. So that's all. Thank you.
Okay, so my name is Shai, and I'm going to present about our results and discussion for our full integrated circuit. So we can see here is the PV solar array array. Okay, then here, which is a part for our boost converter, and the part which is behind there is the inverter part. So what are we using is a bipolar PWM, which is bipolar pulse width modulation for our inverter. And so we continue to the next, which is here for the DC converter, what output we get. So as we can see from the graph, we have two output, which is 4 volt and 335 volt. So the input is around 262, which I set it to 262, and it outputs 400 and 335. But we can see that 400 volt have reaches its steady state smoothly with minimal overshoot and very low ripple, indicating a strong voltage regulation. So as we can see, for 325 volts, it experienced a small initial overshoot before stabilizing with slightly more visible ripple. So at last, we chose to use 400 volts for our full integrated circuit because it shows a slightly smoother and more well-damped response. Okay, so move on. So move on, we have this inverter type. So the inverter, we're using the bipolar PWM, right? So the output switches between positive and negative values every cycle. So you can see the high frequency switching pattern where the waveform alternates between the positive and the negative voltage. This switching patterns is then filtered by an LC filter, which is shown in the full integrated circuit. It goes through, it passes by the LC filter in a real system to produce an AC sine wave, which is the last part of our graph. And the purpose of using bipolar PWM is to reduce the harmonic distortion and achieve better control of the output voltage. Okay, so this is the final output that we want to is 230 volt, and we use a 50 hertz frequency for our bipolar PWM. So as we can see, this performs a very stable sinusoidal wave that we want from we inputting the 262 from the PV array, and after that we get a boost converter up to 400 volts, and after that we go through the inverter which transform DC to AC. After that, go through an LC filter. So we get our last graph, which is 230 volt and with a 50 hertz of frequency as stated in our title. So move on. So in conclusion, the project successfully designed and simulate solar power integration system that integrates a PV array, DC-DC boost converter, battery storage, and a single phase inverter which use bipolar pulse width modulation. So the 4.05 kilowatts solar array met the 14 kilowatts per hour daily demand, while the boost converter maintained a stable 400 volt DC for the inverter. So the SPWM controlled the H-bridge inverter supported by an LC filter deliver a clean 230 volt 50 hertz AC output suitable for the irrigation pump. So overall, the system operated reliably in simulation, demonstrating it's practically and sustainable for off-grid agriculture use. So that's all from us. Thank you.